right, welcome back everybody. The topic today is a continuation of what we did last week and before the Easter break. And this is about the implementation of the quantum Fourier transform. And we are going to start looking at one of the important algorithms, which is called the phase estimation algorithm, which we will also use to extract information about eigenvalues and eigenvectors. Now, the focus today will be on us implementing the QFT and also on how we can implement the phase estimation algorithm. I'm mostly going to use the whiteboard, and I would also like to say that after many rounds with myself and input from you people, I've landed on two main projects, or project two main variants. And one of these is about implementing quantum Fourier transforms, extracting the phase estimations and use that to find eigenvalues. So you can compare that with what you did in project one. And then if there is time, we can also look at the implementation of other algorithms like ordering. We can have a factoring if you want to, where quantum Fourier transforms actually enter. And quantum Fourier transforms are actually one of these algorithms which are very important for many quantum computing algorithms. So it's useful to have seen them, yeah? Yeah. Oh, that is when you do the factoring, and then you want to have the right order of the numbers when you factor. You can also do arithmetic additions. And the reason why I bring up these things is that the textbook which we have chosen, this textbook by Hunt, in these sections 6.1 to 6.7, you have this pretty well described. So the kind of idea now is actually to go through some of these elements so that you have everything which is needed for solving project number 2. So in a sense, you can look up software which has been developed by other people, and hopefully that can serve as an example for getting started. So that's roughly the idea. So I'm going to go through some of the technicalities so that you see how you can set up the algorithm. And then how we can do the phase estimation and how we can implement this to find eigenvalues and use, for instance, if we want to implement Shor's algorithm, where we actually use the quantum Fourier transform. Now, the other project is more for people who want to do machine learning. So I will have a project on quantum machine learning, but we may not have time to discuss these things for the rest of the semester. So I will use next week as well to wrap up material on these quantum algorithms. So that means that project 2, there will be one variant, which goes mainly on implementations of important and famous quantum algorithms. And if you scroll down, so what you have here is something which I'm going to repeat quickly. But if you look at the end here, I was thinking of other algorithms like factoring, perhaps quantum search algorithms. And then for the rest of the semester, we could discuss maybe some quantum machine learning algorithms. The problem is that many of you have not taken a course in machine learning. And what you will often see then is that half of the textbooks, or even more than half of the textbooks, cover traditional machine learning methods before they go quantum. So it means that there is quite some thick threshold before you can get started and to appreciate what a quantum machine learning algorithm is about. So last year we had people who were pretty savvy on machine learning, and they actually went on their own and looked at quantum machine learning algorithms. But the population this year, I mean, we are a little bit more scattered as a group. So if somebody wants to do that project, that is something which we will leave more for self-study. I may say something about it, but I was also thinking for the rest of the semester, when we've gone through some of these algorithms by the end of next week, that we actually look at the physical realizations of quantum computers. So that's something which many people actually wonder about. I mean, how do we actually make these gates? What are these gates made up of? So that's another possibility. So just send me some feedback on what you would like to hear. So this will probably be the last 2 lectures which we have. Because after next week, we have roughly 2 or 3 lectures left. And then we're going to use the rest of the semester to work on the projects. Okay, but just send me a message. Just send me an email on what you would like to hear about. Okay. So what I'm going to do now for the rest of the day is basically just switch over to the whiteboard, and we are going to have a quick repetition of what we did last week. So the material you see in the slides here is basically just a reminder of what we did last week. And then we are going to look at how we can implement a quantum Fourier transform. And this is covered by Hunt's textbook. So when you're going to write, if you want to do that project, then you can actually follow step by step what's in the textbook. So hopefully that project is a little bit simpler than the one we had as project number 1. Hopefully, but you never know. Normally, when you make exercises, you always think that you make the simplest possible exercise. And then when the exam is over, the people who went through the exam said, this is the most difficult exam ever. Okay, guys, let me switch over to the whiteboard here. And let's try to go through some of these technicalities. So it's going to be a long list of derivations and technicalities which we need to discuss. So one of the things which we did last time was to represent a given state, which we label as a state J. So let's just put up the header here. We have April. So we represented a state with the label J, and that was a compact notation which we used in order to label a state which could contain many qubits. And this was then given by a subtype of notation where we have this different J0, J2 up to n qubits. So this could be a case, just to remind you of this kind of more compact notation. So we had a case with 2 qubits. Then we could have the state 0, 0. And that means that this is a state which we then would label as state 0. We could have the state 0, 1, which we chose to label as state 1. And similarly, we have the state 1, 0, which we label by, so this is just a hierarchy which we chose, but this hierarchy, you see that immediately how it comes through, because what we are using is a compact bit representation of the states. So the final state is something which we label as state 3. So these numbers which you see here, these ones, they refer to this J which you see here. This J0, J1, etc., which you see here, they refer to these guys. So it means that in this particular case, we have a J0 equal to 0 and J1 equal to 0. In principle, that state is actually given by this tensor product, but we use this kind of compact notation. So you could think of you setting up a kind of table where you have labeled the different states, and then you have pointers which point to the right indices. And what we use then, if we use a integer binary notation, so the J's can take values 0, 1. If you have 3 qubits, you would have a similar situation. We could have the state 0, 0, 0, which is actually 0, tensor product with 0, and tensor product with that one. And then we would use 0 as a notation for that. And that is this index or this label J, which we have in the first equation. Now, if we are using a binary integer notation, then this J can be written out as J0. You can always invert the order between J0 and Jn minus 1. It doesn't matter. You just opt for one ordering of the bits. So it's common to have the most significant first, and then the less significant, etc., etc., etc. So in this case, if you have an integer representation, you use this one. And then you have plus a J1 of 2 of n minus 2 plus plus plus, and then you end up with a Jn minus 2 of 2 to the power of 1, plus finally a Jn minus 1 times 2 to the power of 0. So this is the kind of notation you can use. However, when we set up this state last time, this state J, we found a very compact notation in terms of the Fourier transform on a basis state. So the discrete Fourier transform, or what became the quantum Fourier transform, was given by 1 divided by 2, and then we have the square root of n, the number of qubits. And 2 to the power of little n is the same as the number of configurations which we have. And this was given by the tensor product from m equals 0. So this is roughly where we ended last week. And then we have a tensor product of this linear combination. And we have an e of I of 2 pi and j. And this is multiplied with 2 to the power of minus m, multiplied with 1. And this was the way we could actually rewrite the Fourier transform, the discrete Fourier transform, in terms of what we call the quantum Fourier transform. So this is basically a transformation which involves rotations of specific states. So this was a compact notation. And what it means is simply that we have 1, this is just an element of repetition from last week. And then we have all these states, 0 plus e of I of 2 pi. And what I'm doing now is just to set up these divisions here, because when we are setting up these, you will see that instead of using an integer representation for the state J, it's going to be convenient to use a floating point binary representation. And you will see that in just a few moments. Why we change from this notation, which is an integer representation, to an integer binary representation, to a floating binary representation. So this is now given by 1. And then we have this chain of tensor products. So we have 0, of e of 2 pi, and then we have a j. So let me just rewrite that a little bit. This is j divided by 2 to the power of 1 of 1. And then we have this long, long chain of tensor products. And then we have the final one, which is 0 plus e of I of 2 pi. And then we have a j divided by 2 to the power of n minus 1. And this is a 1. And finally, we have end of the parenthesis here. So you see now that instead of dealing with the operation which you see here, this one and that one and that one, we can introduce a more compact notation where we simply rewrite what we had here as a floating point representation for our binary numbers. So what we do then is that we define, and now I'm just setting up for a specific value of n. It doesn't need to be the 0th qubit, it can be a qubit m. And this now goes like j of n plus 1, and it continues all the way up to j of n minus 1. And this is given by Jn of 2 to the power of -1. That's the first. So this is just a floating point representation, a binary representation, okay? So when you convert from a decimal representation to a binary, you know that they're not all numbers you can represent with a finite number of the bits. So if you take 0.1, 1 divided by 10, you cannot represent that exactly in a computer with a finite number of bits. So that will always be approximated. This is important, so just keep that in mind, that the kind of approximation we are doing now in terms of a number of bits is something which is going to be important when we are going to use the phase estimation algorithm to find the eigenvalues. Because then we are going to use a finite amount of bits and no qubits, and this finite amount of qubits is going to define the precision of the eigenvalues which we're going to extract. Okay, so let me just continue this one. So this is plus, and I hope everybody's gotten it, so I can switch side. So I would have a j of n plus 1 of 2 minus 2, and this goes all the way up to j of n minus 1. And then this is multiplied with 2 of minus n minus m. And I have assumed that n is larger than m. So you can, that means that if you look back at that state, which we defined, this state j, we had a more compact notation so that you don't need to have j divided by a number. You introduce that immediately. So you have a j0. So these are the different qubits which you have up to a j of n minus 1. This has a more compact notation, which now runs like 1 over square root of 2 to the power of n. And then I have the different states here, which I now I'm rewriting in a more compact way, 2 pi. And then I have 0 of j n minus 1 of 1. Tensor product with 0 of e of I of 2 pi, and then I have the next one, which is j of n minus 2 of j n minus 1. And I'm going to just write down what this means at the end for you. But you saw that already in the previous definition, which we have here. You see now what this actually stands for. And this is then given by the final one, where we have a qubit 0 plus an e of I of 2 pi of 0. And then we have all the qubits from J0, J1, J2 up to Jn minus 1. And this is multiplied with 1. And then this is a little bit strange notation because the parenthesis doesn't fit properly on my whiteboard. But this is the more compact notation. So just keep in mind that something which we wrote like J0 divided by 2 is actually equal to 0, J0. When I have 0, J0, J1, that is the same as J0 divided by 2 plus J1, 1 divided by 2 to the power of 2. So if I only have one number, if you have one number only, that means one bit. This is also for something which is going to come a little bit later. So if I have only one bit, then we are going to actually look at the phase estimation for one bit only. In that case, you know that J0 is either 0 or 1. That means that the number you can represent, so suppose now that you only have one bit to deal with, you have a 1-bit computer. So a 1-bit computer allows you to represent 0, because then J0 is 0. So this is binary numbers, 0 and 1, and 0.5. So these are the only numbers, the floating point numbers, if you have 1 bit, which you can represent in a computer. If, yeah? Oh, yeah, sorry. Let me just move that one down here. Okay. And if you have 2 bits, classical bits, then you see that you get 0, you get 0.5, you get 0.25, and you have 0.75. So with 2 qubits, you can represent 4 floating point numbers. And the more you move on, the more floating point numbers you can represent. But just keep in mind that the number of bits you have now, when we're going to translate this into an algorithm for finding the energies, the number of bits defines the precision of the energy. Yeah?
In the fifth example, I could only represent 0.25, 0.5, and 0.75.
Yeah, yeah.
So if I want to represent 0.6,
you couldn't do that.
More bits that I can find
yeah.
your combination.
Yeah. Exactly. Yeah. So you actually have a formula for given a given number of bits, how many floating point numbers you can represent. So what you see here is just us. So you could have kept this kind of representation, which we used last week. I mean, this representation here, which is just a straightforward write-out of the quantum Fourier transform. But then since we have all these divisions with j divided by a power of 2, then it's more handy to rewrite it in terms of this compact notation. And this kind of compact notation is also going to be very handy when we are going to look at how we represent this in terms of rotation matrices, because we are going to build some circuits which are going to represent these things. More questions? So I hope you see the link here. This is just a compact notation, but it's going to be important for us when we are going to visualize and set up the different circuits and gates. So also keep in mind that if you look at the way I've defined the sequence of bits, you can always encode it the other way around. You don't need to start with J0. You could start with Jn minus 1. There's nothing which hinders you doing that. So you decide what is the least significant and what is the most significant bit. And this is the same when you do representations of real numbers. So that is just there's just going to be a notational difference whether you want to encode it like J0, J1, J2 up to Jn minus 1, or if you want to do Jn minus 1, Jn minus 2, and all the way down to J1 and J0. That's just going to bring in a notational difference. And you decide what is the most significant bit, which represents the largest part of the fraction. This is the same when you're dealing with floating point representations in a computer. So adding a phase, this is something which we need to look a little bit at now, because what you see when you look at the quantum Fourier transform, there is something which goes like e to the power of something, of I 2 pi, multiplied with some kind of fraction. And this is going to represent specific rotations. And some time ago, I think it was very much in the beginning of the semester, we defined the so-called rotation matrices. So let's take a look at that and just bring back the kind of things which we looked at in the beginning of the semester. So if I now take a rotation by, so let's just remind ourselves about rotations. And when we look at rotations, it's always good to have to remind ourselves about this famous relation here. I think it's called Euler's relation of cosine phi plus I of sine of phi. And then we know that E of pi half is equal to I. And that corresponds to a rotation of 90 degrees. And this is counterclockwise. Let me set up a graph here. So if you're here now, and then you rotate an angle phi, and you rotate at the pi half, you're rotating in this direction. So this will be counterclockwise. Similarly, if I have E of I of pi, this is something which is equal to -1. And that corresponds to 180 degrees counterclockwise. And similarly, if I do I of 3 pi half, we know that that one is equal to -I. And that corresponds to either 270 counterclockwise or 90 degrees clockwise. Because then we are just in, if we do a rotation of 270, we can go all the way around to here, or we can follow the clock and go this way. Okay, I hope you don't get offended if I bring up this kind of equations here, huh? Because it's a little bit important for kind of a more overarching understanding. So a rotation of, let's say, 180 degrees, that would be a fraction of 2 pi in this expression of e to the 2 pi of I, and so on. And then you can set up all kinds of rotations here. So, and some rotations, like if you have a rotation of 135 degrees, you can put that together as a rotation of 90 degrees plus a rotation of 45 degrees. And then you can just put this as a product of rotations. So when we are setting up a Fourier transform, so let's now look at this for 2 qubits, just to get a little bit a feeling of what we need to program when we are implementing the quantum Fourier transform. So the quantum Fourier transform for 2 qubits, and we went through some of these things last time. And what we have then is something which we could now set up. We could assume this is just an example I'm setting up. So suppose now you have qubit 0. And we know that the first operation, which we have, if we look back here, if we look at this one, this is normally represented by a Hadamard gate operating on the first qubit. So if we now take this expression, which we have, we can then write this as a Hadamard gate acting on it. Then, and here's an important thing, which becomes, when we're looking at this rotation, we can actually have a rotation on the second qubit, or we can just leave it on the first qubit. It's going to give the same result, and you will see why. So this is the first qubit, so we can just call this qubit 0. And then we have the next one, which we could leave in a state 1 if we want to. Just to give you an example, it could be 0. So this is just an example I'm putting up. So this is the second qubit, which we label as qubit 1. Now, what we have then after this operation is that we get a new state, which is psi 1 here. So the initial state, which we start with here, this state psi. So psi is just the tensor product of 0 with 1. Okay? And now we perform a Hadamard operation, and I'm going to set up these operations. When I look at the Fourier transform, I can think of qubit 0 as a control qubit. And then that means that the rotation, which I have now, because if you look at the first one, this would typically give just 0. So you would have E1 here. So you have 0 plus 1, which is a Hadamard gate. And then if I look at the second one here, that is going to give me a rotation. So if we now look at this one, we would write this in terms of a so-called S gate or rotation gate. You will often see this as an S or as an R gate. But this is a so-called phase gate. So this one gives us now a state psi 2 here. And if I take the first one, so this psi 1, that is nothing but H, the Hadamard gate. And now we have to be very careful because this is a 2 by 2. So it acts on 1 qubit. And this is a tensor product with the identity matrix, which acts on the second qubit and doesn't do anything. So this will be also 2 by 2 matrix. And this is acting on the initial state, which we just labeled 0, 1. So if we take this one, we're going to use this kind of compact notation here, 0, 1. So if I now write it out, this will be given by, and I'm going to spell it out a little bit differently. So that gives us 0 plus 1. And then we have the tensor product with the other qubit, which is a 1 here. So instead of using the compact notation, I'm trying to keep some of the tensor product just to see that we are going to operate with given qubits here. Now, in the next case, the first qubit is left unchanged. And that means that this state psi 2 here is going now to be given by the state which I had, this 1 over 2. And then I have my 0 tensor product with 1. So nothing happens with that one because the 0, 1 is the control bit. But then I have plus, and then I have the 1 qubit. And this is now multiplied with this S matrix. So this becomes a tensor product with this S acting on the 1 qubit, the other one. And if I now write this out, since this S matrix, which you have here, this S, when I'm looking up the Fourier transform, this is just going to be this matrix here of E of I of pi divided by 2 times 1. And the thing which is interesting here is that the state 1, so sorry, this is not that one, I was a little bit too quick here. S acting on 1 is given by that. So the thing which is interesting here and why I could actually have let the S operation act on the first qubit is simply because the state 1 is actually an eigenstate of this matrix S. And you see that this one just becomes equal to the state E of I of pi divided by 2 multiplied with 1. So that means that when I set up the operation here, what I get is the following. So I end up with a state psi 2 here. And this is the implementation of the Fourier transform, the quantum Fourier transform on 2 qubits. And this is the way I would actually set up the circuit. So the state psi 2, which I have here, is then given by 1 over square root of 2. And then I have a state 0 tensor product with 1 plus, and since this is just a constant, or it just becomes an E of pi half, it could actually have acted on the first qubit. And we would often rewrite this in terms of 1 over square root of 2 of 0, 0 plus, and this is the compact notation of I pi half of 1, 1. Now I could actually have had the second qubit as my control qubit. And I could have performed the same operation on the first qubit. And I would have gotten exactly the same. And this is simply because this E of I pi half, or this S matrix, has the computational basis as an eigenbasis. Okay? So it's important to keep in mind in connection with the so-called phase estimation algorithm. And this feature which you see now is something which we are going to use when we look at the phase estimation algorithm here. What we say is also, you will find this as a kind of jargon in the literature, is that I never liked that actually, when you look at this operation here, you're kicking the phase into qubit, the first qubit. So it's often also called a kick operation or kick phase. It's just a kind of naming, because the way you operate on the states means that you can place this operation on the first qubits or on the second qubit. So one of the things which I just wanted to remind you of is the set of rotation gates, or rotations circuits, as we also label them. So we have an RK, a 2 by 2 matrix. And this is now given by 1, 0, and then we have 0 of e of 2 pi of I divided by 2 to the power of k. So that obviously means that if I have r of k equals 0, that is simply equal to 1, 0, 0, and then I have e of 2 pi of I, which is equal to 1. So that's pretty easy. If I have rk equal to 1, this is another one which you will see many, many times, then you would get that this is the same as 0 of e of 2 pi of I divided by 2, etc., etc. So these are some of the basic operations which we are going to look at. And when we now are setting up this kind of 2-qubit gates in order to see how we can do the calculation here, there's another thing which we need to think of, and that is that we also want to make measurements at the end. So when we make a measurement, information about these phases which we have, that is actually lost. So the phase estimation algorithm which we discussed, which we mentioned, is a way to gain this information about the phase of the state which we have. So let's now look at a 2-qubit gate in order to see how we would set up the final QFT. So what you saw here is just parts of the QFT algorithm, because if you look back at the operation we had, the mathematical expression, if you spell this out for 2 qubits, you will see now that from this graph, which I put up here, there is a Hadamard operation which is missing on the second qubit. So the full QFT circuit, the way we would set it up, so let's just put this up here. So the full QFT for 2 qubits, I'm going to guide you through some examples here so that you get some familiarity with it. And when you've seen these examples, it should be pretty obvious how you are going to write your own code for a quantum Fourier transform. So essentially what I'm doing here is I'm following what's in the textbook by Hunt, which you also have access to via the university library. So if I do the full QFT for 2 qubits, what I could do now is to start just with an example. So let's go through the basic mathematics here. So we could start with 0, 0, which is just a tensor product of 2 qubit zeros. So that's the initial state which I'm preparing. And what I would have then is a qubit 0 here. So that is I'm going to label this for a psi 0. So this is my state, psi 0. Then what I have is a Hadamard operation. When you look at the expressions for the Fourier transforms, the first thing which takes place is a Hadamard transformation on the first qubit. And then I get a linear combination. So these Fourier transforms are actually rotations. So you have your computational basis with 0 points up and 1 points down, north and south if you prefer. And then you perform a Hadamard transformations and you rotate. And that means that you get a mixing between 0 and 1. And this defines the next state. So nothing happens with the second qubit. So I get a psi 1. Then I can either have the first qubit as a control qubit or the second one. And now I perform a rotation with an S gate here. And in that case, I have a rotation on an angle pi half. And this is the same, this quantity you see here is the same as an R1, which we mentioned previously. Then, when we do that, so this is marked like this, then we get a new state, which we just call psi 2 here. And then we have a Hadamard on the second qubit. And that is the final implementation of all the mathematical expressions which we have. And this gives me the final state, psi of 3. That one. That is the circuit representation of the Hadamard gate. So I could actually have changed this control operation. So this gate, which you see here, is called a control R or control U. There also you have the U gates. So this operation here, let's just single this one out. So this is normally called a control R gate. So one of the qubits is unchanged, and then some operation is done on the second qubit. This operation here, due to the fact that the states 0 and 1 are eigenstates of this rotation matrix, this R1 matrix, that means that I could actually have performed the same operation on the first qubit. So I could actually have interchanged what is the control qubit with the operation on a specific qubit. And I would have gotten the same result, as you also saw that previously. So what I wanted to do next now is simply just to set up what you get when you perform all these operations here. So let's just take a look at the final result before we take a small break. So in our case now, what we have is obviously that this psi 0 in this specific case is just 0, 0. And we write that out in a more compact way, like 0, 0. Then this psi 1 is again just the Hadamard gate, tensor product with the identity. So the way it's set up now means that the Hadamard acts on the first qubit and the identity acts on the second qubit. So this is now a 4x4 matrix. And this is then multiplied with 0, 0. And when I do the operations, this becomes equal to 0, 0 plus, and then I have 1, 0 divided by the square root of 2. And then when I apply the S gate in this specific case, because the value which I'm implementing now, so the operation of the S gate, in this specific case, since we have a qubit 0, which is the qubit I'm testing it on, it just gives the same state. So this has just a psi 1. Nothing happens. And then finally, when I look at psi 3 here, this is now a Hadamard gate, which is acting on the second qubit. And when I do the operation here, so this is acting now on psi 2. And that gives me simply, when I write everything out, and this is something which we discussed last week as well. So I get plus 0, 1, and then I get plus 1, 0, and I get plus 1, 1. So what I've done now, I've transformed an original state, 0, 0, into a linear combination of the computational basis states for 2 qubits. You can do the same thing in case your psi 0, and I'm just going to write them down. Suppose that is equal to 0, 1. Then what you will find is that psi 3, when you perform these operations, is given by 1/2 of 0, 0 minus 0, 1 plus I of 1, 0, and then I have minus I of 1, 1. And then I can actually set up everything, but the way I can think of this is that the new state which I'm getting, or the state I started with, let me just, and then we're going to take a break here. This J transforms the original state, transforms via QFT, and that QFT matrix for the 2 qubit case is given by the following. So you would have an initial state, you multiply it with. So this is transformed by the QFT matrix, which acts on that state, 1, 1, 1. Remember, we set up this matrix, and we could actually rewrite that in terms, no, this is minus 1, I, and minus I, and then I, minus 1, minus 1, and then I have minus 1, minus I, and I. And what we typically have used is actually this, if you remember back, we defined this quantity 2 pi I divided by, no, I think it's just 2 pi of I. not pi of I, sorry. It was pi of I. I never remember how we defined it. Let me just look up what I wrote last time. Yeah, it's I divided by 2 pi, 2 to the power of n. Yeah, that's the quantity. Okay, so in the 2 by 2 case, we have an explicit matrix, which we can set up. So when you are writing your first QFT code, the quantum Fourier transform, you can compare the results with the multiplication of that matrix against an initial state. So if I take if the state J is equal to, let's say, 0, 0, like I get here, and that state, just to remind you of that one, is just a vector of length 4. In that particular case, what I have with a QFT matrix, I have this matrix you see here. I multiply that matrix with this state here. And for that specific state, which I start with, I get this transformed state here. If I take this state here and I multiply with that matrix, I'm going to get this linear combination of computational basis states. So this is essentially what the QFT is doing for us. So the first part of the second project, if you find that interesting, is actually to write such a QFT transformation. And then you have a useful check for 2 qubits, 3 qubits, and whatever. We are going to, after the break, we are going to look at the 3 qubit case and just see what this matrix looks like and what the circuit could look like, so that you get some kind of feeling on how to write these different circuits. So now the full circuit for the 2 qubit case is given by what you see here. And that's a very handy representation of all these mathematical operations. I went a little bit over time, which means that we